The trajectory of the Apollo lunar lander enforces zero velocity at touchdown. Conversely, this kingfisher dives into the water to capture its prey. It enters approximately normal, just as this gull. Or, like this brown pelican, this falcon approaches the ground at incidence for prey capture, while this Falcon 9 rocket landing, combines multiple objectives: a ground normal touchdown with zero velocity and at a specific location. Sometimes you get lucky with your trajectory, but when we can't rely on luck, we rely on guidance laws to achieve our trajectory objectives, whether it be normal impact, impact at incidence, or normal touchdown. These cases involve trajectory shaping guidance that mold the flight path to meet specific objectives beyond just reaching the endpoint. Our goal is to learn methods to derive optimal trajectory shaping guidance laws and explore their application. Here we'll explore terminal attitude constrained guidance, which allows hitting the endpoint at a specific body orientation, like the pelican or the falcon. Consider the pursuer has its velocity vector always out its nose so that the angle of attack is always zero. And suppose the vehicle is above the ground, some initial altitude, and that we desire to fly to a point downrange and impact the ground at a specific angle. Now, to achieve our desired terminal state, the vehicle can maneuver or accelerate normal to its velocity vector. And to pull these G's, the vehicle changes its attitude. To change its attitude, the vehicle uses control surfaces like fins. Therefore, we'll need to connect the fin action to the G's pulled. So we turn to the vehicle dynamics, where our objective is to derive the essential pitch dynamics to formulate a tractable problem statement. Here's the linearized angle of attack equation. We've already assumed that the angle of attack is zero, so that alpha and alpha dot can be eliminated. Also, we'll assume the term ZQ over V is negligible, since that ratio is often small for cylindrical bodies. Eliminating this term from the equation, we're left with pitch rate, which is equal to theta dot, is equal to minus Z del E over V times del E. This is an essential pitch equation. Also, acceleration is linearly related to angle of attack and elevator displacement. So, we cancel the angle of attack term, leaving acceleration as a function of elevator displacement. These equations combined constitute a linear time-invariant state-space system that is the plant dynamics for our guidance law development. For brevity, we've defined Ka as minus Z del E over V and Kb as Z del E. Also, U is assigned del E. Now we need to derive tractable engagement kinematics for guidance law development. To do this, we're going to assume all angles in the engagement are small so that the engagement behaves in approximately a linear fashion. Under this assumption, vertical motion is approximately minus Vp times t plus the initial altitude h, which makes the rate of descent Vp, which makes the vertical acceleration of the pursuer 0. In the horizontal plane, we work in terms of relative motion, with xr equal to xt minus xp. We look to derive now the relative horizontal acceleration. Horizontal acceleration is ap times cosine theta, and we determined ap as kb times u, so that the horizontal acceleration is kb times cosine of theta times u. Now we can determine xr double dot as xt double dot minus kb cosine theta times u. We assume target acceleration is 0 in the horizontal direction. Therefore, we have our expression for relative horizontal acceleration. If theta is small, then this expression is approximately minus kb times u, a linear expression. Or, if we want to make theta some representative pitch angle for the engagement, then we can use a theta star. The horizontal acceleration and the pitch equation constitute our state equations for guidance law development, along with the acceleration output equation. We'll write this as a set of linear time-invariant equations for relative position, relative velocity, and pitch angle. And in matrix form, we then obtain the LTI system. In summary, it captures the kinematics of the engagement and the pitch dynamics. We're now ready to pose the problem statement. Our problem objective is to find the control signal that minimizes control effort while hitting the desired point, normal or perpendicular to the ground. Let's translate this statement mathematically. Find the control signal over T0 to TF. That is, we're looking for a control signal that accomplishes our objective over a finite time interval. Next, we seek to minimize control effort, where here, effort means the square integral of the control input. We seek to intercept the target, meaning that at the final time, or at the time of intercept, the horizontal distance between the pursuer and target is 0. And then normal to the ground, simply theta at TF is 0, where theta is reference to the vertical inertial axis. We can wrap all these goals up into a single function j, a cost function, where the more we meet the objectives, the smaller j is. Therefore, our problem statement becomes to find the control signal over the finite time interval that minimizes the cost function while subject to the kinematic and dynamic state equations. The state equations are in the standard x dot is ax plus bu form, and so we can more succinctly write the problem statement. The cost function can be written in matrix form as well, where M is the terminal penalty matrix, Q the state penalty matrix, and R the control penalty matrix. These penalty matrices are often parameterized, as they are here with gamma and beta, to place different emphasis on the regulation of specific states or control inputs. The problem statement is now in a standard recognizable form as a finite horizon linear quadratic regulator problem. There's a significant body of literature that allows us to solve these types of optimal control problems. Briefly, the optimal control is determined as minus R inverse B transpose times a matrix P of T times X of T. This is a state feedback law, where the three pre-multiplying matrices constitute a matrix of time-varying gains. To determine the time-varying gains, clearly we need to know P of T, and that's the solution to an algebraic Riccati equation, a set of differential equations in this case, that integrates backward in time, where we know the final time condition from the matrix M. Analytically solving the differential algebraic Riccati equation can be a complex task. I've done it before by transforming time to go so that it's a forward integration problem, and then solving something called the matrix Hamiltonian. Instead of doing that here, I want to take a different approach that uses something called the Cauchy-Schwarz inequality. This approach is used by Paul Zarkan in his book, Tactical and Strategic Missile Guidance. Consider x and y that are functions of time, defined over the time interval t0 to tf. We assume that the signals x and y are square integrable, and therefore belong to the Hilbert space L2, meaning that the integral of the square of the modulus of x is finite. Now, if the signal x or y are real valued, then it reduces to the square integral being finite. The L2 space has an inner product. It generalizes the Euclidean dot product to functions in L2. And this extends the notion of an angle between two vectors to two L2 functions. In addition to this inner product, we can also establish a notion of length or size with a norm. The L2 norm of x is the square root of the inner product of x with itself. Now, the Cauchy-Schwarz inequality can be applied to scalars, vectors, and functions like x and y that we've assumed here. It says that the modulus of the inner product of those two signals x and y is bounded by the product of the norm of x with the norm of y. And in addition to the Cauchy-Schwarz inequality, we're going to use a corollary that when x and y are linearly dependent, the inequality in Cauchy-Schwarz becomes an equality. Okay, so how can these preliminaries help us solve optimization problems? We're going to solve a special case of this terminal attitude guidance problem with Cauchy-Schwarz. First, we're going to need to solve the state equations. The solution of that LTI system can be obtained with the fundamental matrix phi. We determine the fundamental matrix from the inverse Laplace transform of the resolvent of the matrix A. And we determine the resolvent of A with the adjoint formula. Applying the adjoint formula, we get the resolvent. Then applying the inverse Laplace transform to each element, we get the fundamental matrix. Now written in terms of time to go, Tf minus T, we substitute phi into our LTI solution. For brevity, we assign B2 and B3 to the 2 and 3 elements in the B matrix. This solution on the bottom contains the space of all possible solutions for all initial conditions for all square integrable control inputs. And inside of that space is the optimal guidance law that we desire. To get at that optimal guidance law, recall we have a couple terminal constraints to enforce, and we'll use those to narrow down our solution space. Those constraints pertained to the miss distance and the terminal attitude. So let's work with XR and theta equations. In the miss distance equation, note on the right-hand side, we have zero effort miss. We'll denote this as Z going forward. Now, we can make a hard enforcement of the terminal constraints in these expressions. This simply involves setting XR to 0, and if we were only interested in ground normal impact, then we would set theta at TF to 0 as well. This step is a departure from the LQR solution. Cost functions are created when we cannot perfectly achieve all objectives. The tuning of penalties in the cost function allows us to balance competing objectives of minimizing control effort while meeting the terminal miss and attitude objectives. But here, we're making a hard enforcement of the terminal constraints. Now, hold on to this idea because I want to step back with the terminal pitch angle equation. Instead of enforcing terminal pitch to 0, we could easily define terminal pitch angle error, E theta. Effectively then building a command for terminal pitch angle into our future guidance law. Now, we seek to enforce zero miss and theta approaching the desired pitch angle at theta TF. For a little more brevity, I'm going to let capital B2 be lowercase b2 times TF minus tau. And when we do this, we get a beautiful set of equations to work with. With the constraints now built in, we seek to find the control that minimizes the control effort while satisfying the above relations. Now, these are linear expressions, and so we can linearly combine them with, say, a variable lambda into a single expression. And then squaring each side, we see the control effort appear. Now, recall the Cauchy-Schwarz inequality. Applying it to our expression, we find that zero effort miss and pitch error are bounded by the norms of control effectiveness, that's what's in the B vector, and the control input U. Of course, we can manipulate this expression now to convey a lower bound on control effort. So we seek to find a control that achieves this lower bound, that is the minimal control effort. Toward this, let's determine the parameter lambda that minimizes E. So we first expand the denominator and observe a few norms that will use the norm nomenclature for notational brevity. And then back to our inequality. The inequality with control effort E is minimized when it's equal. Therefore, we find the lambda for E that provides zero slope, the minimum of E with respect to lambda. To evaluate the derivative, let's let D be the denominator, and then applying the derivative operation, we get the expression. We want to work with the numerator. Let's factor out what we can, and now solve for the roots of the numerator. There's the numerator, substitute in D, expand, cancel terms. We get a new expression, and we can still simplify this a little more. So ultimately we get, look, a linear expression for lambda that we can easily then solve for the lambda that minimizes the control effort. Back to the Cauchy-Schwarz inequality. Note that we assumed linear dependence between x and y in the process of minimizing E. So if we determine k and then use that linear dependence, we determine the minimal control effort in the guidance law. So from our application of Cauchy-Schwarz, we have x and y noted. Our guidance law becomes the linear feedback law in this abstract form. Now we wish to solve for k. To do this, substitute the linear expression for u into our zero effort miss expression, and then solve for k. Let's use the norm notation for brevity. Now take that k and substitute it into our optimal guidance law. And recall, we've already determined lambda. So substitute lambda in as well, and we get a fairly complex expression. Let's work to simplify this a bit. First, let's find common denominators in the numerator and in the denominator. And note, those are actually the same up top and bottom. Cancel them out. And we can also cancel out a z over z and a couple more terms in the denominator, and this leaves us with a guidance law. And it's still in an abstract form, but with the feedback variables, zero effort miss z, and pitch angle error E theta now more prominently shown in the numerator. To get at the law, we're going to need to evaluate the norms. And we can recall all of the things that go inside those norms. So let's evaluate them. Integrate the norm of B3 squared, and we get K squared times time to go, where again time to go is TF minus T. The norm of capital B2 squared gives another expression in terms of time to go, and the norm of B2 times B3, yet another time to go expression. Let's substitute these variables into our guidance law formula. We obtain then an expression with a bunch of time to go terms. Grouping like terms in the numerator and then working out common denominators in the coefficients, and now simplifying those coefficients, and now canceling terms, divide by KB, divide by KA, divide by time to go squared, we get an even simpler expression. Break it out into two terms and we get a main result. We get a proportional navigation term on the left and a terminal attitude enforcement term on the right. That second term is our trajectory shaping term. Interestingly, we have optimal gains of 6 and 2. And we can introduce a navigation gain, n, if tuning of the guidance law is desired, where n equals 6 is optimal. Also, note the inverse dependence on Ka and Kb. These represent pitch control effectiveness on pitch angle and acceleration. The guidance law is telling us that if the effectiveness on acceleration is large, that is Kb is large, then less homing effort is actually necessary. So Kb being large scales down that homing effort term, that pronav term. If control effectiveness on pitch is relatively large, then less guidance effort toward the terminal attitude is necessary by similar reasoning. Now this law outputs a control effect, fin deflection as we've framed it here. More typically, guidance laws will output acceleration commands. And since we have our acceleration formula, which simply multiplies u by kb, we multiply throughout by kb to obtain the acceleration form of the terminal attitude guidance law. This removes the kb dependence in the pronav term, and in the second term we now have the ratio of kb to ka. And remember what kb and ka are. Because when you divide kb by ka, clearly we're left with minus vp. So the acceleration form of the guidance law now does not depend on that control effectiveness derivative. And we can further generalize the law for the gain n, where n6 is optimal. We just derived a command terminal attitude guidance law with the Cauchy-Schwarz inequality. The authors, Kim and Greider, started with a similar problem statement, but solved their guidance problem with linear quadratic methods. As you will see, our solution differs from theirs, but we would like to find some connection between our results. Here's our problem statement, which Kim and Greider solved using linear quadratic methods. Their solution is a state feedback law with time-varying coefficients, where each coefficient is quite a complicated expression involving the penalty parameters beta and gamma. They observed that the time-varying coefficients changed significantly in time as time approached TF, or time to go, went to 0. This meant that accurate time to go would be necessary. And while it would be tempting to set each coefficient to a constant value, it was found that doing so significantly degraded the guidance law performance. Finally, the result is limited to ground normal intercept. Now, as in the derivation with other optimal guidance laws like proportional navigation and augmented pronav, we investigate the case of taking limits on penalty parameters in the cost function, and here particularly on the terminal attitude objective by letting gamma go to infinity. The way we interpret this is we put as much emphasis on the terminal attitude objective as possible, while still minimizing control effort and trying to intercept the target. Here's the first time-varying coefficient in their solution. Divide all terms by gamma and take the limit as gamma goes to infinity while holding beta to 0. This allows us to cancel many terms, leaving 6 over kb times time to go squared. Taking the same limit for the other coefficients yields significantly simplified expressions as well. Now, substitute the coefficients back into the state feedback law, and we get a guidance law that's greatly simplified and has 3 terms. And note the first 2 terms on the right-hand side can be combined to form zero effort miss in the numerator. And once we put in Z for zero effort miss, we recognize this looks awfully familiar. It's the same as our result, just with the command pitch angle of 0 for ground normal impact. In our Cauchy-Schwarz solution, we made a hard enforcement of the terminal conditions. The equivalent of this in the LQR solution is to take the limit of the terminal attitude penalty. And you may also be wondering if we took the limit of the control effort penalty, beta. Letting beta go to infinity, though, causes U to go to 0 for all time. The solution degenerates. Let's summarize the guidance law results. We had our derivation with a Cauchy-Schwarz inequality, where we allowed a commanded attitude to enter the guidance law. We had our result by taking limits in Kim and Greider's LQR solution. It's exactly the same as our law, but just for the case of normal intercept. And of course, there's Kim and Greider's LQR solution itself. We will compare these laws in simulation and we'll plot them as enumerated in the color of their numbers. Here's the ground plane and the target. The pursuer travels at 200 feet per second and is initially 10 degrees from the vertical. Its altitude is 12,000 feet, and it seeks to intercept the target that's 2,000 feet downrange, perpendicular to the ground. We'll also use the values of KB and KA used in Greider, but our initial conditions are different than in their study. Here, we're trying to keep angles small to preserve linearity of the engagement, which was behind our guidance law derivation. This allows us to clearly assess whether or not our guidance law is successful. Do we get zero miss and the terminal attitude we desired? Our linear simulation proceeds with the definition of initial conditions, the state equations being integrated forward in time, the state variables being fed back to the guidance law, so that fin angle is updated, input back to the state equations, and the process continues until the pursuer passes zero altitude, at which point the simulation stops. This animation shows the trajectory produced from our derived guidance law. It seems clear the guidance law is trying to work toward the objective. The trajectory overshoots the target, curving back in to hit it, apparently at a slightly negative incidence. And we would like to understand why the trajectory is not perpendicular to the ground as being commanded. Since velocity is assumed at the nose of the pursuer, tangent lines to the flight path also indicate pitch angle is slightly negative at impact in this simulation. Now we plot each guidance law and overlay their velocity vectors. We have identical agreement. We observe velocity vector orientation and therefore pitch angle closely approaches zero despite not being tangent to the path. I believe this can be attributed to the linear simulation. You see, vertical velocity is not in the state equation. It's assumed to be velocity magnitude because we assume that pitch angle was small. This will be investigated in further detail. We plot the pitch angle directly from the state equation and find our simulation successfully approaches zero pitch, not asymptotically, but in a smooth, parabolic and direct manner. The zero effort miss also approaches zero, indicating the vehicle achieves its terminal objective to hit the target. The miss distance is 0.13 feet, which presumably will get more accurate as the simulation time step size decreases. This is the guidance fin command that is input to the plant pitch dynamics. The control reverses sign at 20 seconds so that essentially the vehicle is accelerating in one direction and then another. We should also be concerned with the magnitude of the control input. Note that Ka and Kb have units, and if those units are in radians, this output would be unrealistic for a fin deflection. We also observe essentially linear guidance command, apart from some transients near intercept. Let's explore this control reversal in a little more detail. The reversal coincides with a change in slope of the pitch angle, or a change in sign of the pitch rate, so that the vehicle is turning in one direction, then begins to turn in an opposite direction. I would expect this to cause an inflection in the trajectory curve somewhere around here, but it's hard to tell from this plot. Is inflection in the trajectory a characteristic feature of terminal attitude trajectory shaping guidance? At this point, we have several research questions, so we move on from this initial phase of observations to developing and testing hypotheses. We would like to know first if the angle of attack is 0 as we assumed. The test is to compute angle of attack from the simulation data. That is, we will compute flight path angle reference to the vertical line, then we compute angle of attack from the flight path angle gamma and the pitch angle theta. Finally, we plot the angle of attack versus time. Now, since the guidance laws produce similar results, we only plot results for our derived guidance law, number 1. The curved lines are the pitch and the flight path angle. They overlay so that the dashed green line is the angle of attack steady at 0. And indeed, angle of attack is nearly double machine precision at 10 to the minus 14. So we conclude that angle of attack is 0 as we assumed. Next, we would like to understand why the velocity vector was not tangent to the flight path. Our hypothesis is that the small pitch angle assumption in the development of the linear simulation is the cause of the discrepancy. To test this, we compare the cases where the small angle assumption is on, where since theta is small, cosine of theta is 1 and sine of theta is 0, to the case of where cosine and sine of theta are evaluated. Here's the trajectory for the small angle assumption on, as we previously simulated. Here's the trajectory for the small angle assumption off. There's no apparent difference, so we conclude the small pitch angle assumption is not the cause of the velocity vector being misaligned with the flight path as required by the physics, by the kinematics. My next hypothesis is that a 2D nonlinear simulation would more accurately capture the velocity. So I incorporated the terminal attitude guidance law into a planar nonlinear simulation. Here's the linear simulation from our initial study without the velocity vector tangent to the flight path. And here's the nonlinear simulation. Now, clearly, the velocity vector is tangent. This confirms our hypothesis. At this point, I had a sinking feeling that perhaps this law would only be useful for engagements where all angles were small, even possibly smaller than the angles we've examined in this case. I wondered if this meant that the 0 angle of attack assumption in the nonlinear simulation would be violated. So here's the linear simulation as previously shown, clearly confirming 0 angle of attack. And here's the same plot for the nonlinear simulation. The pitch angle objective is still met, but the flight path angle is different from the pitch angle, so that significant non-zero angle of attack occurs. But before moving on, I wondered if the pitch control effectiveness was simply too small to achieve the terminal attitude constraint. Even though I knew that small Ka would scale up the terminal attitude term, I still wanted to explore it. And this was before I realized that the law is independent of z del E as we showed in its acceleration command form. So this question led me to think about Ka and Kb more, because I realized that while Kim and Greider assigned values to Ka and Kb, we showed how they were connected to the pitch dynamics of an aircraft and shared a common z-del-E controlled derivative. So I speculated there was an inconsistency between the engagement kinematics and the pitch dynamics. And to make it consistent, we needed to use a common z-del-E as well as a common velocity between the pitch equations and the engagement equations. To test this, I decided to find reasonable values of z-del-E and v and use these in our simulation. Looking to textbooks, I found z-del-E of -75 with units of radians, and velocity of 800 feet per second is plausible for a missile, so that Ka is 0.93 and Kb is 75. Performing the linear simulation, we now observe the trajectory does not overshoot and appears to intercept normal to the ground. The nonlinear simulation seems identical by inspection. Suddenly things seem to be performing better. Does this update better preserve the zero angle of attack assumption? Here's the nonlinear simulation now. Note that the pitch angle goes to 0 as specified, and that small bias in the angle of attack is due to about a 1 degree mismatch between the flight path angle and the pitch angle. So I conclude something that's rather obvious. The physics of the vehicle dynamics cannot be arbitrarily specified, and that the velocity in Ka in the pitch dynamics should be the same velocity that's used in the engagement simulation of the kinematics of the pursuer. Further, the control inputs now are within reasonable limits, and the transients have essentially vanished. Now, back to the original question. We find that so long as the formulas we derive for Ka and Kb are followed, one can scale up or scale down pitch effectiveness z-del-E without any effect on the trajectory. But we note that there's a physical limit to fin deflection. That is, the guidance law command. And once realistic control limits are placed in the simulation, the pursuer performance can vary if z-del-E is so small that unrealistic control effects are required. Now we go back to the question of what causes the overshoot. We saw overshoot in the first example. Then we updated our simulation so that the parameters defining the engagement kinematics and the pitch dynamics were consistent. And we found that overshoot no longer occurred for ground normal intercept. The updated scenario confirms that overshoot is not necessarily a feature of normal attitude impact. Let's now explore non-zero terminal attitude commands. Note that impacting while pointing rightward is positive and leftward is negative. Here's the case of commanding negative 10 degrees and negative 20 degrees and negative 30 degrees. So we conclude that while trajectory overshoot is not necessarily a feature of normal attitude impact, it is a requirement for negative attitude impact, because a reverse turn will always be necessary to accomplish a negative attitude. And this is particularly true since angle of attack is 0 and the body pitch angle is aligned then with the velocity vector. Let's now revisit the question of control reversal. What causes this reversal, and is it a characteristic of the terminal attitude constraint? I speculate that control reversal is necessary due to competing terminal objectives of hitting the target with a desired attitude. To test this, I simulated several terminal attitudes and explored the fin control time history. This positive 30-degree terminal attitude trajectory involves an initial turn down and then turn out to 30 degrees. This Normal terminal attitude trajectory, as we've seen before, roughly holds the same initial pitch, then turns down to the target. And this negative 30-degree terminal attitude turns out to pass the target with enough time to turn back into the target. Let's look at the guidance command for numerous terminal attitude cases. This is the guidance command or control input versus time. Control reversal is present for all cases. And while it still reverses, the control is nearly zero for the commanded terminal 10-degree attitude, where the pursuer flies almost in a straight line to the target because the initial and final pitch angles are 10 degrees. Here's the corresponding pitch angle versus time. For terminal attitude of 0 and attitude becoming more negative, we observe an increasing initial positive pitch right maneuver, followed by its negative pitch left maneuver. And for positive terminal attitude, we observe the opposite, an initial pitch left maneuver, followed by a pitch right maneuver to turn into the target. Take the terminal attitude of positive 30 degrees, for example. The elevator goes trailing edge down to pitch the vehicle downward initially. As the vehicle approaches the target, the elevator deflects positive, trailing edge up, pitching the vehicle counterclockwise to the right to achieve the desired 30-degree terminal attitude. When ground normal intercept is desired, the elevator deflects trailing edge up to pitch the vehicle counterclockwise initially to the right. As the target is approached, the vehicle turns down, clockwise, with trailing edge deflected downward, ultimately to achieve the ground normal intercept. For a minus 30-degree desired terminal attitude, the vehicle requires the largest elevator deflection up to pitch the vehicle counterclockwise to over 20 degrees from the vertical reference line. Then it executes a clockwise turn down, left maneuver into the terminal negative 30-degree attitude. And it's interesting that this control reversal happens near the same point in time, which means that the pitch above or below the initial pitch angle as the vehicle turns to the desired attitude will also occur near the common point in time. We won't investigate this point further, but back to the question of whether control reversal is characteristic of the terminal attitude constraint. We found that all cases exhibited control reversal and fell into one of two categories. The first is when the terminal attitude is less than the initial attitude. In this case, a pitch up and then pitch down maneuver was executed. The second is when the terminal attitude is greater than the initial attitude. In this case, the vehicle pitches down, then up. There's roughly an intermediate case where the terminal attitude is the initial attitude. In conclusion, it's clear that control reversal creates the required pitch action to meet the terminal attitude objective for a single target location, which confirms our hypothesis. Finally, we explore transients that are observed in some control signals around the final time. Take, for instance, this 30-degree terminal attitude case for the nonlinear simulation. These abrupt transients appear near the final time. I believe it's because time to go approaches 0 and causes divide by 0 then in the guidance law. So to test this, I'm going to look at the terms in the guidance law and identify specifically which ones are diverging and causing the spikes. Here's the nonlinear planar state simulation data over the last 4 time steps. The first column is time, the second, target flight path angle, then target X and Y, horizontal and vertical positions, Note, the target was given a very small velocity and attitude to avoid singularities in this simulation, but effectively the target is static because it moves less than 0.2 of an inch over the course of the engagement. Both horizontal and vertical target and pursuer velocities are captured here. The final time, RP2 equals 0, or vertical position of the pursuer just touches the ground. At 15.46 seconds, we observe the pursuer goes from being 3 feet from the target to suddenly 30 feet above it. At 15.46 seconds, the pursuer also passes the target. Associated with this abrupt change is a sign change in the pursuer vertical and horizontal velocity components. The target is at the origin, so the pursuer passing the target or moving toward and then away is a sign change in the velocity. Finally, we note the pitch angle diverges from 0.5 to 3,000 radians between 15.45 and 15.46 seconds. Given the resolution of our time step size, the closest thing we have to TF is 15.45 seconds. This data indicates there's some unknown instability that's happening after TF. We won't explore this further here, but my next step would be to inspect the variables in the numerical integrator just before, at, and after TF. Here, our objective is to identify what terms are causing the spikes in the control signal. It's the second term. Due to order 1000 pitch angle, order 10 to the minus 1 Ka, and order 10 to the minus 2 time to go. Note in this time to go plot, our time to go estimate, which is just range over closing velocity, and the actual time to go, using 15.45 seconds, are in good agreement. Therefore, we found that time to go contributed, but was not the primary cause of the divergence. The spikes are caused by pitch angle divergence after the final time due to some unknown instability in the simulation. This phenomena where the pursuer bounces off the target in a non-physical manner is commonly observed in engagement simulations. It's interesting and not fully understood to me at this time. Many animals and engineered vehicles reach a specific endpoint while meeting other objectives related to attitude or velocity. These are examples of trajectory shaping guidance, which generally molds the vehicle flight path to meet objectives beyond just reaching that desired endpoint. Our goal was to learn how to derive optimal trajectory shaping guidance laws and to explore their application. We worked from a scenario that was like the apparent behaviors of pelicans, falcons, and other birds of prey, where target capture at a particular body angle was desired. We worked from a problem statement that was consistent with Kim and Grider, published in 1973, but we used Cauchy-Schwarz to derive our guidance law from that problem statement, and we built in the ability to command a specific terminal attitude. Kim and Grider applied linear quadratic methods to derive their guidance law, but we showed that actually the laws were connected through the case of infinite terminal attitude effort applied through the terminal attitude penalty. Through simulation, we found the guidance laws were effective, and that despite their differences, the guidance laws actually performed similarly. Now, key to ensuring effectiveness of the guidance law was to consistently use z-del-e and pursuer velocity in the pitch equations and the kinematic equations. For all cases examined, we found that path inflection was characteristic of the pursuer trajectory and a feature related to achieving the terminal objective. We also showed that beyond the linear simulation, the guidance laws were successful in the nonlinear sim, producing identical trajectories. Future work could examine the effect of fin or acceleration limits on the pursuer, the effect of time delays in the homing loop associated with an autopilot, and scenarios that may introduce more kinematic nonlinearity in the engagement. Access this lesson and more at learngnc.com. If you're a Patreon subscriber, thank you very much for your support. Your contributions keep the content coming, keep the website learngnc.com up and running without ads. That's all for now. Thanks for watching. We'll see you in the next lesson.